One time I trained from 2:30 to 10.
What are you training for?
I once worked 6 a.m. to 8 a.m.
Yeah, what? I'm gonna pretend I know what that is.
I got paid for the rest.
14-hour shifts?
Yeah.
Is that illegal?
You know, like learn how to make all the drinks. Yeah, there's actually espresso shots.
Right, right.
That would stress me out so much.
How much-
I hope you all at the end take an espresso shot.
That was worth it.
Sit in.
Was it a day?
All right,
Where'd you go? Probably not the rest.
let's take a look at
Try.
what we have to do for today. So a quick little summary of what we did yesterday, at least from the idea of the first derivative test. Optimization is an easy application and extension of the basic differentiation and our first derivative test. Why do we use the first derivative test? Well, with optimization, what we want to do is manipulate our multiple equations until we have only one dependent and one independent. Have to have one and only one independent, only one and one dependent. The primary equation's minimum maximum value can then be found by taking our derivative. Why are we doing that? We're critical numbers, right? What are the critical numbers? Critical numbers are the zeros or the does not exist of the graph. Not sure where, or the equation, or the, yeah, of the, we can say graph, or more precise would be the primary equation. Not sure where that went. Primary equation. The critical numbers are possible locations of a relative extreme. The first derivative test determines a critical number value as a MAC when the sign changes. And then a min when we change from negative to positive. Okay, and if that's the only place, then it's an absolute. If it's not the only place, then we need to compare. Okay, which leads us to, is it closed? Could we use the EBT for that? Yeah.
You have another piece of paper to do all these questions. 'Cause that doesn't really look like a lot.
Yes, I think that would be an awesome idea.
We can say
That's okay.
that.
That's okay. That's okay. So let's start off with an open boxed top. And some of you may remember this one from Algebra 2. So we have an open box top made by cutting congruent squares of side length X from the corners of a 20 by 25 sheet. Okay. So I've got this sheet that I start out with that is 20 in this direction and 25 in that direction. And what do I do with it? I come in here and I cut out little squares.
This looks familiar.
Yes, I knew it would. Yes,
Not the box.
we're going to call this a length of X here. And of course, this one would be X, that one would be X, that one would be X, and so forth. Okay. And what's going to happen is we're going to fold each one of these tabs up, and that's going to form our open box top. Okay. If I needed a top for this, what would I have to do? How would this change my diagram if I had needed a top? Yeah, I'd have to have another fold for that. So I'd have another flap, maybe out this way or up this way. So kind of imagine if they did ask you one that did have a top to it. Okay. it would have to have another one that would come over and be the exact same size of our base. So whatever that is, we would have to fold that over, but we don't. We're an open top box. Now, what's it tell us about this? How large will the squares be to make the box hold as much as possible? Okay, as much as possible. And then it says, what's the resulting maximum volume? So they kind of give it away with the part B. What are we trying to maximize? Yes, okay. So we're going to try and maximize our volume, which means we need a volume equation. What's our volume equation going to be? Well, let's just keep it simple. Length times width times height, and that's of this box. Now we've got one dependent variable. We got three independent variables here. Okay, so we've got to eliminate. How are we going to eliminate the L, W, and H so there's just one variable? Hopefully you can see when this folds up, the easy dimensions or the easy dimension is our height, right? When we fold this thing up, might look a little bit like this. And we can see that that X, whatever this X is going to be how high that is. Yeah. So that's the easy one. What about the length and the width? What will they become?
Is it 2x minus
2x minus.
20 minus 2x, 25 minus 2x.
Yeah, it's the other way around, right? This should be 25 minus the two x's we cut off on either end. And this will be the 20 minus the two, bless you, the two x's on either end. So this would be a volume equals 25 minus 2x and a 20 minus 2x times an x. Will I do anything more with that? No, because this one's definitely going to be a calculator-driven problem. I don't want to mess up. Okay, so no, go right to my calculator. Now, before I do that, I do want to domain this. What is our domain? Okay, who's the one that said, hey, I'm having trouble with my domain? Okay, so what's the minimum value that X can be?
0.
0. Now, does it make a box?
No.
Not really. Okay, so, you know, it's kind of one of those iffy ones of, all right, now here's my justification for, hey, I'm going to close it. Does it tell me I have to have a certain volume? No. So theoretically, can I have a volume of 0 if I wanted to? Yes. Pretty lame box, but I know X can't be negative. Okay, but I could just have a flat little box there. So let's make that 0, because again, if I can close it, it just saves me some trouble. Okay? It makes me know for sure I don't have to check for 2 or 3 different possibles. Okay. Now, what will be the maximum that X will be?
2 million.
Why 10 and not 2 million?
10 is your next 0.
Why is that my next 0?
Because if you said 20 minus 2 equals 0.
Okay, can you see what happens to this length here when X equals 10? Yeah, so. Which means we can do what? Yes, we can say this. Since V of X is continuous on, and I'll just put the closed interval, the EVT applies. Or however you like to say it. If you've got the Mia stamp, whatever that says. Okay. Which means we're going to go right to our calculator and let the calculator do the talking. V prime equals 0. V prime does not exist. Go ahead and do this one, get a little practice.
You gotta like move the X match.
Yeah, the nice thing about having that domain, if we wanted to, we could set our window before we even graph it. So we're going to our y equal. And again, I'm just putting it in exactly the way I've got it written on my paper, not worrying about any distributing. Making sure I have some parentheses. Not factoring anything out. N times x. Does that look good? And again, just so that I don't have to wait on the graph, and because I don't want to get mixed up with it, I'm going to turn that one off. And like I said, I'm just going to go in here and change my window. I usually like to go a little bit beyond just to get a picture of it. So rather than go 0 to 10, I'll just go -5 and +15. I'm 5 on either side. My y, let's just, again, I'll go -10. I can go -5, -1 if I wanted to. I could keep it at 40 also, but I'm just going to graph this guy.
Mr. Don,
Yes, what happened?
how do you do the derivative on like the older ones? I forget.
On the older ones?
What do you want?
Well, that's not what I got.
Is that not what we're gonna? Yeah, when you do map 8 on the older one. Let's see if this works for us. Okay, so it's gonna have what is it, n derive will show up, and of course I would choose red. And then you're going to put your y1 x comma x. Close the comma. Or close the parentheses. And that will work. Okay. So again, and just think of it exactly the way we would do it on the new ones. The first thing you would enter would be your y1. And then it gives us an x and then x over there too. So you're entering the same thing, just done that way. All right. And next thing I want to do is I want to find my zeros. Okay. And let's take a look at those. This is 1, 2, 3. Oh, let me just do it.
Second 0 not 5 is not the domain.
Yes.
Yep.
But what if we didn't do that?
Second calc. Oh, well, let me do this one real quickly. We're looking for a 0. And again, you can arrow over, or you can enter a number in there. I could probably just put 3 since I just counted. So, oops, went too far, didn't I? I want a positive number. Far. I don't even see my Frogger there. There he is. Okay, so now I know I'm above, and you can kind of see it's coming down from the left to the right, positive to negative. Sounds like a minimum. And then arrow to the right of it. I've got a negative number there. Boom, boom. And I probably should have made my window a little bit better to see that. But now when I press enter, we get a 0 of 3.6811, and I can stop there since that's 4 decimals. Okay. And then, yes, the question begs, what about this guy over here? Well, notice where I am when I get to here. I'm at the end of my domain at 10. And also notice the value on it is going from negative to positive, meaning that, oops, yeah, we were looking for, that's the min. I think I said wrong before, but yeah, so that's a minimum, not a maximum. We were looking for a maximum volume. So no need to even consider that one. Okay, and of course we have a no on our does not exist, which means now we're ready for our applying our EBT. And applying the EBT will give us, or we'll use the 0 and the 10 and this 3.6811. We already looked at that and knew that. And again, that's why I like to use EBT, because sometimes those endpoints are really easy to calculate. And I'm going to do it the easy way on my calculator. Second quit, bars, Y bars, and use my functionation here and just put the 3.6811. And all I have to do is make sure this is a positive value. Okay. If it was just part A on this, I just have to make sure it's a positive value. But then I could just put positive there. But in this case, I'm going to go ahead and put that number in since I did go ahead and calculate it. And we notice that our part A is that. So let's make sure we answer both of those. And I think the best way to answer both of those is just in one statement. And that would be, again, what did they say? They said, how large should the squares be to make the boxes hold as much as possible? So I'll say the squares should be, or should have, I'll just put it like this, should be 3.6811. I forgot to put my units down. Inches in length. And will result in a max volume of, say here, 8 to 0.528. Don't need that extra one. If I had the extra one, it wouldn't count against me though. Inches cubed. Not so bad. Sure.
Would it matter if you said in width?
Yeah, I mean, it's implied that's a square. You're going to have equal length and width. You could put, you should cut out a square that's 3.6811 by 3.6811.
So you can't put.
However you want. I mean, again, there's certain things that we know our reader should know, and that's a reader should know what a square is. So I don't have to go that extra distance. All right, let's take a look at the next one. Hiker finds herself in a forest 2 miles from the nearest point on a straight road. She wants to walk to her car that is parked 10 miles down the road. If she can walk 4 miles per hour along the road, but only 3 miles an hour through the forest, toward what point on the road should she walk in order to reach the car in the least amount of time? Okay, our classic problem that you'll find in every calculus book that looks like this. We've got our little hiker. She's out here and she is 2 miles from a road that, if we travel on that road, is 10 miles long before she gets to her car. Now, she's given the opportunity to walk anywhere along this road. She could walk just like this and reach this point. And then she would have to go along the road this length. And if she wanted to, she could walk straight to the road and do this, and then walk the full 10 miles, or she could walk no distance along the road, right? She could go and do everything out in the woods. It's like a nature girl, okay? Why should I go on the road when I can just spend all my time in the nature? Okay, so she has that option to us, but you'll see here that she does walk at different rates as she's going through this. She can walk 4 4 miles per hour along the road. Okay, 4 miles per hour along the road would be this here. Okay, so that's just kind of note that this traveling along this will be at 4 miles per hour. Through the woods, she's a little bit slower, and it's going to be at a rate of 3 miles per hour through the woods. We travel that one. And now we get to the point of let's use our calculus, because it says, let's do this in the least amount of time, which sounds like we need to optimize what? A minimum time. So we're looking to minimize our time. And now look at our diagram. Is there a time anywhere on our diagram? Yeah, we do have that in our rate, but does our graph measure any time here? No. Okay. So are we trying to then minimize distance here? Not really, because the minimum distance between the two would be a straight line, but that doesn't guarantee that that's going to be the fastest. Okay, so we do need to take this geometry and change it over into a time. So we do have this rate here that we're traveling. Okay, now when I taught middle school, we used to do these distance rate and time problems. And I always did them like this. I'd have them draw a circle and then put a D here and an R and a T and drew it like that. So that way they understood what we do with a distance with given rate and time, because now they have the understanding that distance always equals whatever rate you have times your time. Distance equals rate times time. Okay, you're going 50 miles per hour and you drive for 2 hours. How long did you go? Or how far did you go? 100 miles. Okay, if you went 200 miles and you traveled at a rate of 50 miles per hour, what was the time? 4 hours. Okay, and that's what I teach them with this is, hey, you know what? If I'm doing my distance, I'm just going to take these two guys, and since they're right across from each other, I'm going to multiply it. If I want to find another one, such as the time you just did, I'm going to take the distance and divide it by rate. Just like, hey, guess what? If I traveled 400 miles and it took me 8 hours, how would I find my rate? 400 divided by the time, distance divided by time gives me the rate, right? So it's all based upon this one here, okay? Which now tells me, you know what? My equation, since I'm trying to maximize time, should probably look like what? Shouldn't this be very good? Okay, I need to divide by my rate. So time would equal that distance divided by whatever rate that I had. Wait a second here, I have 2 rates. Well, I have 2 rates, and won't I even have 2 distances? One of those distances, we'll call this one D1, will be strictly in the woods. So won't we take that distance and divide that by the rate that we're traveling during the woods? And then once we reach the road, we can start our distance measurement all over again. And this one would be D2. And we'll divide that by our rate. Okay. So in this particular problem, we know we're trying to minimize time, so we don't want to change that one. And the nice thing is, both of these denominators we know. Don't we know that this rate is 3? And we know that this rate is 4. Now we need to get just one variable in our numerator. Okay? And what I want to introduce is this length from here to here, and let's call that x. I like to choose that distance for the x rather than the other one, just because it just kind of helps out a little bit, but with the math. So let's take a look at what D1 will be. If x is this here, what will D1 be? What expression could we write for that? X squared plus 4, square root of it. Just Pythagorean theorem here. We know we have a right triangle here. So this is x squared plus 4. We'll take the square root of that, and we don't have to worry about positives or negatives because we know we're only dealing with positives. So we can substitute that in here for our D1, x squared plus 4. And now, what will D2 be? Just 10 minus x, right? Because we know once we reach this point on the road, it's 10 miles away. So any distance x is just going to lessen what that is. So yes, D2 is simply 10 minus x, 10 minus x. Look what we have. We have an equation with our optimization variable and only one other variable on the other side. Okay. Again, domain this. What will our domain be here? Okay. Can x be 0? Wasn't that the very first case we talked about, is she could just walk straight to the road and x would be 0. So x could be 0. What's the maximum x could be? 10. That was the other extreme where she walked completely through the woods and not in the road. One of them when she walks the complete distance of the road, x, and one when she doesn't walk on the road at all, which sure looks like EBT applies, blah, blah, blah. Again, okay on your notes, couple of homework, but make sure on a test quiz you fill that in. Which means now we can go right to our calculator, substitute this in, and we're going to go t prime equals 0. T prime does not exist. Does not exist gives us nothing. And this one, just like the last time, only gives us one critical number on our domain, and it's this. Okay. Which means we are going to go right to our EBT applies. We have, in this case, 0, a 10, and a 2.2677. Okay. Those endpoints could be possibilities. So this is our time. This is our, I'm sorry, this is our x. This one is the time. Okay. So what I would need to do is put those in my calculator. I could kind of do some calculations up there, but anyway, what did this give me here? We got 3.1666, a 2.9409, and a 3.3999, which you can see gives us the smallest amount of time as this one. Okay, now let's reread our question. Was it asking us what is the fastest time? No, or what would be the least amount of time? Yes. Oh, wait a second. It says toward what point on the road should she walk? So I need to decide what that is. And to make it simpler in my description, here's what I'm going to do. I'm going to take and find D2. by taking 10 minus that x of 2.2677, and that resulted in 7.732 miles. When you see my answer, you'll know why I did that simple little calculation. Okay, because now when I answer this, the hiker should walk to a point on the road 7.732 miles from the car. I don't have to write as much as if I had to describe this X value. I'd have to say she'd have to walk this many miles from a point directly across from her as she walks through the woods, 10 miles from the car. Okay, and this is just kind of hard to write when I can just easily say, hey, let's just walk this far from the car on the road. Okay, and again, it's just one simple little calculation. So all good? All right, let's take a look at our next one. The next one says, campsite in a forest is 2 miles from the nearest point on a straight road. A pond is 10 miles down the road. If it costs 4 miles, or $4 per mile to ride along the road and $3 per mile through the forest, towards what point on the road should we ride in order to minimize the cost to ride to the pond? So some reason they set this up as a little toll road, and we can imagine this. And here's what our picture looks like. It looks like this. We have a little spot that we're sitting up here, and we got our campsite. Our little tent is here. Woo-hoo. And it's 2 miles off of the road, and the road is 10 miles from the pond. And we need to decide at what point along this road should we go that is going to, in this case, minimize our cost. Minimize our cost. Okay. Now, we could walk straight out of the forest and then the complete length of the road, or we could just ride, I guess it was ride is what it said. We could ride directly to the pond over here. Which means we could set it up to look something like this, because don't we have two distances here? We have a distance that we would go through the woods, and we have a distance here that we would travel along the road. This one, of course, would result in, since that's 10 miles, this distance here would be 10 minus X. Or wait a second here, isn't this the exact same problem we had before?
Yeah.
As a matter of fact, yeah, shouldn't we maybe even get the exact same answer? Because let's look at their numbers here.
Different answer, different number.
It is $3 per mile in the forest, and it is $4 per mile along the road.
Can we look at rate instead of time?
Yeah, okay. Now, both of these were rates. Isn't miles per hour a rate? And isn't dollars per mile a rate? But we're trying to minimize our cost. So will our cost be calculated by the same thing we did here? A distance divided by this rate? No. Okay, does that ever work? If it costs $3 per hamburger, do you take how many hamburgers you want and divide it by $3? No, you do what? Yes, this is a multiplication problem. Yes, these are two problems, both of which have a rate in them, but No, our cost is going to be, in the first case, $3 per mile times our distance one, right? Number of miles. And then what are we going to add to that? We're going to add to that our $4 per mile times our distance two. Why aren't we dividing them? Because again, this distance is in miles. This distance here is in miles. Dollars per mile times miles gives us dollars. That distance equals rate divided or times time resulted in a division problem to maximize or minimize our time. This one is a multiplication problem. Everything else in the geometry is exactly the same. If we try and do this one, like we did the hiker problem, we're in big trouble. If we try and do the hiker problem, like we did this one, we're in big trouble. Okay. Even though we can look at this and say, yep, the geometry is going to work out exactly the same. So that we'll have this 3 times the square root of x squared plus 4, and then 4 times the quantity of x minus, or excuse me, 10 minus x. So again, our D1 is that Pythagorean theorem with the x squared plus 4. Our D2 is the 10 minus x. And then I'm just going to stop that one there because the rest is all the same. We know that our domain would be the exact same. 0 to 10, our EVT applies. We would go in here and do the cost equaling 0. Cost does not exist. Oops, got that in the wrong space. Does not exist, blah, blah, blah. This would be when x equals some number. We would do our table with 0, whatever critical number this is. $10, and then we would choose the one that was the smallest, and it would be this guy right here, based upon what we have. Okay, so again, this putting in our calculator is going to look exactly like the other. It's the setup that I wanted to look at on this one. Okay, let's take a look at the next one. Next one says you must construct a rain gutter from a sheet of metal that's 12 inches wide. And if you ever seen how they do them now, they used to make them all and then send them, and now they have the machines out there on the truck, and it's just a flat piece of metal. They run it through and it just bends up the sides, and you can do the gutter. And that's how they do the seamless gutters now. So that's basically what we have. We have this 12-foot wide sheet of metal that we're going to run through a machine, and it's going to fold it up into a gutter. Okay, so I'll go ahead and try and put it on the same sheet and see what we have here. Okay, so we have, what color? We'll do this one. Okay, so we've got a base down here. I'll call this base 1. And then we've got some flaps that are being folded up. We're going to end up with both of those flaps have to be the same length. And both of these have to be the same length here. And then we'll have a length up here. I'll call this one base 2. 1/3 of the material's width on each side is bent up through an angle of theta. So this angle here is theta. It's going to bend that piece up. Look at that shape there as it gets bent up. And then it did say it's 1/3 of the material. So if we start out with a 12 inch wide, 1/3 of 12 is 4. So I know this length here is 4, that length there is 4. And as a matter of fact, if these both are 4, then this has to be 4. So by that 1/3 statement, I get a couple dimensions that will always be there, okay? Not going to be variables, okay? And I just put this on there just for clarification. Okay? Now it says, how large should the angle be made in the corner to maximize the area of the trapezoidal cross section? So you can see it gives us a dead giveaway that we're trying to maximize area. And since this is a trapezoid, what would every middle schooler say the area formula is? Very good. Okay, so this is going to be a 1/2, and I'm going to put my parentheses right here and our H. And of course, this would be a B1 plus a B2. Okay. Now, part of this we already know. Don't we know what B1 will be? So that one's gone. We only have 2 variables, the B2 and the H, that we need to write in the form of just 1 variable. Okay, so I'm going to take a look at this one and look at this triangle here. This is 4, and this angle here will also be theta if I look at it like this. So I'm looking at this triangle here. This, of course, would be the height that I'm putting right here. Okay. And let me introduce a variable. I'll call this length up there x. And as I look at that, if that is x, then let me draw another triangle over here that you can kind of see. We know that this length here is going to be what? 4. Okay, so I'm going to go ahead and write an equation for B. I'll just put it up here so I can see it real easily. This was again an x, and this is an x. Won't B be equal to 4 plus the 2 x's that we have? As that gets folded up farther and farther, those x's are going to get smaller and smaller. As it goes down, those x's are going to get bigger and bigger. Okay. All right. Whew. Looking at this, and one thing I need to notice is that it did say at what angle theta should I use this. So really what I need is I need to get rid of this B2 and this H by writing theta in there. So that way I can maximize or minimize that theta value, right? So let's take a look at this triangle. Is there a way I could write an equation that, very good, I like that. So the cosine of theta equals x over 4, which would mean that x would equal 4 cosine of theta. Now I can write my equation for B with the theta in there. So I'm going to go back up here. Area equals 1/2. My B1 was 4 plus, this is all of B, 4 plus, and then can I do that math in my head? 2 times the, so this would be a 4 cosine theta. Okay. I'm doing is using this formula, and then I've substituted this in for the x. Okay. That takes care of the B2 in there, but now I still have the H. What could I write to get rid of my H and have a theta in there? Yes, this is an opposite. So the sine of theta would equal the opposite H divided by the hypotenuse 4, which means we could find H by doing 4 times the sine of theta. So this would be times 4 sine theta. Love it? Now, personally, I'd probably clean this up a little bit. What's half of 4? 2. So 2 sine of theta, and then inside the parentheses, I'd have a 4 plus 4, which is a 16, plus 8 cosine theta. I have no idea. I did a multiplication when I should have added. So 4 plus 4 is still 8, not 16, no matter how much I wanted it to be. Okay. And, you know, if I wanted to factor out the 8 now that I see it there, and that would just be a, what, a 1 plus cosine theta. Okay. All right, now, before we go to do our A prime equals 0 and our A prime does not exist, what should we be doing? Domain. And what would make sense for our domain? And we're domaining which variable? We're domaining theta. 0. And then we're not going degrees here. Okay, now, should I stop a little bit sooner than that? Logically, we're trying to maximize our cross-sectional area. So as I'm folding these up, should I go all the way to 180? Okay, where should I probably stop? At 90 degrees or how many radians? Because can you see where now we know just by logic, we're going to get a smaller one. So we know we should stop there. Okay. Again, just using a little bit to save us some time. So yeah, let's just domain this to 1/2 of pi, which means EBT applies. And when I did put this in the calculator, I got a theta of 1.0471, which actually is 1/3 of pi if you would have done it the calculation another way. So these two are the same values. I'll put theta 1, just so it doesn't look like there's 2 of those. And there is no does not exist. Now we're ready to do our EBT table. We're going to put 0 and 1/2 of pi and our 1/3 of pi. And as a result, we had 0 area when we laid it out flat. The cross-sectional area was 20.784 at 1/3 pi, and then it's exactly 16. Just a square, 4 by 4, when we are at 1/2 of pi, which means we can say the angle should be 1/3 radians for a max area of 20.784. And I believe it should be inches squared. And you'll also see I added an extra statement just to play it safe. Did it ask for what the maximum area is? Yeah, but if I wouldn't have read it correctly, I wouldn't have missed the point. Okay, I had to calculate it anyway using my EBT, so why not put it down there? If I didn't state it, I might not get that point if it were asked. All right. Let's take a look at our next one. We're going to construct, or no, this one's a right cylindrical package can have a maximum combined height and perimeter of a cross section of 185 inches. Assuming circular cross sections, what dimension of the package will maximize our volume? So what in the world do we have here? We have a cylinder. Well, let's draw a beautiful little cylinder. We have a radius on that will change if we want to change the package. And we have a height. Beginning, it gave it away by saying, hey, let's do a maximum volume. The volume for this guy, cylinder, is pi r squared times h. And then it gives this weird thing. I'm not sure whose idea was to do this, but they did it and we got to follow. It says we have to have a combined height plus perimeter that equals 185 inches. Okay, so h plus the perimeter. Well, what's the perimeter of that cross section going to be? It's just plain old circumference, right? Which would be 2 pi r equaling 185. Okay. So why did they need to do that? Well, they needed to give us something because you can look at this. This volume would have an infinite number of ways of putting r and h in here that we couldn't get rid of one or the other in this problem. Okay, so which one you think we should eliminate here? Okay, again, it doesn't say find r, find h. It says find the dimensions. Okay, so pick the easiest one. And yes, I believe the easiest one for us to eliminate would be the h. And even looking at this equation over here, it looks real simple to find h just by taking that circumference and subtracting it from 185, which means our volume equation would be pi r squared times 185 minus 2 pi r. Okay. Now we need to look at the domain. It doesn't say I have to have a certain volume, so I could do a domain with a radius of 0. Now, what would be the result here of my upper end? Now, this one takes a little bit of forethought for us to think about it, but this equation, again, if it takes too long, just keep it an open one, but this one's not so bad, because if I look at this equation, what would I do to actually find a maximum R value here? Wouldn't that be when h equals 0? So if h equals 0, my radius will be the largest possible. And what expression would I have for that? Yeah, so it's a really weird number, but based upon this, if I have to keep this true, I can't go to infinity. Okay, it has to stop there. Hey, whatever that is, it helps me out because the EBT applies, which means when I go to my V prime equals 0, my V prime does not exist. I'm going to put all that in my calculator. And again, just the interest of time, 19.629 is this value. And again, trust you're able to use your calculators. Now we'll do our Ebt table, which of course is our radius and our volume. We have a 0 and a 185 divided by 2 pi. Both of those at 0 for radius or 0 for height, so I'll have 0 volume in that. And then all we have to do is put our 19.629 in the calculator, and we get 74,645.141 inches cubed. Now I need to read my question, make sure I have it. It says, what are the dimensions of the package? So the dimensions will be dimensions of radius equals 19.629 inches and a height. Oh, wait a second, we don't have that yet. Where am I going to go to get that? This guy right here problem, right? So actually, we'll use this one. And when I substituted that in, I got a value of 61.667 inches. Dimensions of a radius equal this, and a height of that will have a max volume of the 74,645.141 inches cubed. So again, I did the same thing again, added that on there just to make sure. I've got my, also notice I do have my units. Okay. That will be a point on many of your work problems. Yeah. We're going to keep moving on. This time we've got a solid is formed by a half sphere on the top and the bottom of a right cylinder and total volume of 50 cubic inches. What is the radius of the cylinder so that the total surface area is minimized? So total surface area is minimized by having a cylinder topped off with half of a sphere. And on the bottom is the other half of that sphere. We're asked to minimize our surface area. Surface area for this, I'll have to think a little bit. Well, first of all, I know since the top and the bottom is a sphere, that our surface area is going to be 4 pi r squared, because that's the surface area of a sphere. Half on top, half on bottom. Okay. Now, what will we do for this other part here? Well, that is just the lateral area of a cylinder, which is 2 pi r times h. We don't have to worry about the two circles that would have been on the top and the bottom of this cylinder because those aren't on the surface. They're not the surface material here. Okay. So what dimensions will minimize, oops, assuming cross, there we go. What is the radius so that the total surface area is minimized? Now, they also provide us with a little information here because we need to get this to either an R or an H. They said the volume must be 50 cubic inches. So now let's think about the volume of this. Well, won't the volume be a whole sphere? We have 2 halves, so this is a 4/3 pi r cubed and a whole cylinder, which is the area of the base pi r squared times h. And this has to equal 50. Now, which one are we going to solve for here? Solve for h. I'm sure everybody would agree. H is going to be 50. First thing we would do, we'd have to subtract the 4/3 pi r cubed and then divide by pi r squared. Yes. Why can't I just move the 3 to the bottom? If I did, the 50 would have to be 150. Okay, so I'd have to factor out a 1/3 out of that. So yeah, if you wanted to, you could, but I'm here to tell you, just keep it simple unless you're having trouble putting in your calculator and need to manipulate it a little bit. Keep it as simple as possible, or keep it like this so you're not making some errors, because this one's going to be a whopper to put in our calculator. Surface area equals 4 pi r squared plus 2 pi r times 50 minus 4/3 pi r cubed divided by pi r squared. Okay, and please, guys, I know I'm skipping the calculator when we're going through these, but you know, you're a generation, or you're one of the first generations to go through the high school where you didn't have the graphing calculator put in your hand immediately when you walked in the door. Okay, past generations didn't have Desmos. Everything was graphing calculator, graphing calculator, graphing calculator. So you're going to make a few more mistakes here that you need to make sure you find as you're doing your homework. Okay, so if you just say, hey, Alex, what did you get for that every time? Then you're going to have a little bit of issue when it comes to the test, and it's not going to, you're just going to get in these weird numbers and say, I know this isn't right, but I can't find my mistake. Most likely because you haven't used your calculator enough. Okay. And so, but anyway, that was the little commentary there. In this case, what should our domain be here? Say that again. Can it be 0 this time? We're kind of locked in here. We do have to have a certain volume, so radius can never be 0. So 1, 2, 3, 4, 5. What are we going to make our domain? Radius is greater than 0. Okay, boom. Don't waste time trying to find it. All else fails, you can use your first derivative test. EBT doesn't apply. I'm not going to have to do a table, but I will have to graph this and look to make sure there's only one. Graph it and see, am I going from positive to negative or negative to positive on this? Okay, so let's put this down here. Surface area prime equals 0 at r equals 2.2853 inches. Surface area prime does not exist. That's the second time I've done that. Is the null set. And if we were to look at our calculator, you would see that the surface area equals 0 and changes sign from negative to positive only at r equals 2.2853 inches. Therefore, this value is radius that will result in an absolute minimum surface area. every time you're optimizing, it's implied you have to justify. They don't have to use the word justify. They most likely will, but they don't have to. Okay, so not so bad. All right. Number 6, the solids formed by adding a half of a sphere to the top. Oh, I just did 6. All right. Now, yeah, that's good. Woo-hoo. Next one says find the point on the curve that is closest to 0.7. Okay. So let's find a point on our curve that is 0, that's closest to 0.7. So what do we have here? This guy, we've got some crazy curve, who knows what it is. And we're seeing how far it is away from this point here, 0.7. Which sounds like when it says we need to find a minimum distance, we're trying to minimize our distance, which begs us to use our distance formula. Distance equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. This is our x1, y1 value. So when we substitute in, this will be distance equals just plain old x squared plus, well, isn't this equation here?
How are you getting the x squared?
How am I getting the x squared?
X squared, x1 squared, the x1 is 0.
So then over here, won't my y2 value be just whatever the y coordinate of this is? So that would be plus the y, oops, why did I put y in there? I don't know. The 3x squared plus the 1/3 or x to the 1/3 power. And then I have to remember that my y1 value of 7, I have to deal with that. So it will be a -7. Domain. X can be greater than 0, probably. Who knows, it might even be less than. So yeah, I'm not sure because I just did a little script. Might X be on this side too over here? Could be. So I'm just going to say domain X is all real, something like that. Okay. So let's go ahead and find d prime equals 0. D prime does not exist. Okay. This ends up being an all set. And no, I'm gonna. Yeah, since you guys, again, need a little practice here. So let's get rid of all that. I'll just put this all in parentheses. We've got the x squared. And then plus in parentheses. Yeah, I probably should have put that in there first. I'm just going to raise it to the 1/2 power. But yeah, you guys put square root first, so it's all underneath there. That would have been a better way. X squared plus the x to the 1/3 power. And I gotta subtract the 7, close the parentheses, square that, then close that parentheses and raise it to the 1/2 power. So yeah, I think the square root doing that first and putting it all under probably was a better way. Let's turn this guy off. That look good. And I'm going to go Zoom 6 and go back because I'm not sure what I'm going to see. And I know I changed it last time. So let's just go back to this and see what it shows. Bada bing, bada boom. How many zeros do we have here? Say that again. Which one are we going to look at? Okay, it's trying to minimize. So we need a minimum, right? A minimum is going to occur at which one of these guys? Possibly. Yeah, we've got two of them, don't we? Do I need to consider this one here? Let me go ahead and zoom in real fast. Zoom in. Boom. Okay. So I've got one that's going to occur here and one that's over there. I know it. Reading Rambell today, isn't it? All right, gang. So yeah, sorry about that time. So if you want to come up here during Rambell, that's fine. All right, go to your second block class. Second block class.